Hello everyone, welcome to this new lecture. In this lecture, we will be discussing rest of the part of the chapter that we had discussed in the previous lecture. That is the charges and electric fields of chapter 1 of class 12 physics. So the rest of the parts are force between multiple charges, electric field, electric flux, and Gauss law. So let's move on to the first part, force between multiple charges. It is just an extension of the Coulomb's law that we had seen, that if two charges are placed at a distance between them, so the force that is acting between them, that is calculated using the Coulomb's law. So for calculating the Coulomb's law, in the previous lecture we had seen that we were taking only two charges Q1 and Q2 that were placed at a distance, certain distance. So suppose if we, instead of just two charges Q1 and Q2, if there are multiple charges, suppose there are Q1, Q3, Q4, Q5. So what will be the combined force acting between these two charges? That is the thing that we are going to discuss now. So suppose there is an XY plane, and there is a charge Q1 that is at a distance of r1 from the origin. Suppose there is a charge Q2 that is at a distance r2 from that origin, and there is a charge Q3 that is at a distance r3 from the origin. So according to the parallelogram law of vector addition, we can find out the resultant force acting on Q1 due to the charges Q2 and Q3. The resultant forces will be acting in these directions. The force on Q1 due to force acting on Q1 due to Q3, and in this direction the force due to Q1 on Q force acting on Q1 due to charge Q2. Sorry for the mistake. So the resultant force will be in this direction, and using the parallelogram law of vector addition, we can find out the resultant force acting on resulting on the Q1 due to both the charges. So let's find out F13 and F12. So force acting on charge Q1 due to charge Q3 will be obviously K into Q1 into Q3 by R square, and the direction of this force will be directed from third charge to the first charge, and the force on charge Q1 due to Q2 will be K of Q1 into Q2 by R square, and the direction of this force will be directed towards the charge Q1 from Q2. So the resultant force will be K of Q1 Q3 by R square R13 vector plus K of Q1 Q2 by R square into R12 vector. We can simplify it as force equal to K of Q1 by R square Q2 R12 cap plus Q3 of R of 12 cap. Sorry, I made a mistake here. The direction will be represented by cap, not vector, because they are denoting the vectors. So this is the resultant force acting on Q1 due to the multiple charges Q2 and Q3. So instead of just Q2 and Q3, if there are n number of charges up to Qn, then the formula will remain the same, but just the Q2 along with Q2 Q3 multiple charges will get added up, and we can just simply write it as Qn r r vector. This is a formula to add up multiple charges if there are multiple charges are present in a system. Okay, so let's move on to the next topic. Next topic is electric field. So to understand electric field, suppose there is a charge q that is placed in vacuum. Sorry, I think the spelling is wrong, but leave it. If there is a if a charge q is placed in a vacuum, and if we bring a small charge q1 near it, then it will then the charge q1 will feel some coulombic force due to the bigger charge q. Okay, so now if we remove the charge q from here, then the force that was getting exerted on the charge smaller charge q, that will not just vanish away. Means up to a certain distance only, when the q1 was brought closer to q, at up to that certain distance only that it will experience some force. If q1 is moved to a very far away distance, then it will not experience any force due to q. So electric field lines are basically are giving an idea that up to what extent or up to what region it can exert its force upon another charges. Okay, so the the electric field lines that are getting radiated from charge q are in this form, let's suppose. So up to its region, up to which it can exert force on another charge when it is brought closer to it, that we are calculating using these electric field lines or the electric field. It gives an idea up to the extent its energy is experienced by another charge, and it is calculated using the formula electric field is equal to k into q, means the charge that is exerting its field, divided by r square. R square is denoting the extent or the space or the region up to which it is impacting its force on other objects. It can be simplified as 1 pi 4 pi epsilon naught r square. So this is the electric field. Next part is electric flux. So it is also the extension of electric field. As we have seen, electric fields are getting generated from a charge. Okay, suppose if we place any object in between, or simply we can say any surface on the direction of this radially moving electric fields, then these fields will pass through this surface. Okay, so the number of these electric field lines that are passing through this surface, that is called electric flux. Once again I will repeat, means when the electric field lines are getting radially generated from any charge, then those electric fields will when these electric fields pass through any surface. So the number of electric field lines that are passing through that surface, that is called electric flux, and it is denoted by del phi. It is denoted by del phi, and its formula is del phi is equal to electric field, means the electric field that is passing through the surface into complete area of the means complete surface area of that object, or the surface area through which that those electric field lines are passing, that is calculated using this del phi. Means del phi is giving us idea of the number of electric field lines that are passing through that surface. Okay, so the extension of this electric flux, we get the derivation of Gauss law. So what is Gauss law? In the previous slide, as we are seeing that electric field lines are passing through a surface. If the surface is any kind of a closed surface, like this is a sphere, and the charge Q is placed inside it. Okay, so the electric field lines will get radiated in all directions. Okay, so the total electric field lines that are passing through this entire surface of this sphere, or is called Gauss law. Or Gauss law, we can simply say that the number of electric field lines that are getting passed or passing through any closed surface or any object, or the number of field lines that are passing through any surface, uh, that is only the Gauss law. Means here we are talking about any closed surface or area. So the formula will remain the same. Del phi is equal to E del S. In case of a sphere, let's derive the Gauss equation. It will be electric field we had already derived as electric field is equal to Q by 4 pi epsilon naught R square. Using this formula, electric field is kq by r square, and del s is the, here we can consider the surface area of the sphere. And the surface area of the sphere is 4 pi r square. We can simplify it as let's write it once again, kq by r square into 4 pi r square. So it will be k is 1 by 4 pi epsilon naught r square into q into 4 pi r square. 4 pi r square cancels out, and so this is the Gauss equation, or the flux that are passing through any a sphere. In the same way, if we consider any other objects like a cuboid or a cube, we can simply calculate it by just by putting the equation of the area regarding the of that object or surface through which the electric fields lines are passing, and we can derive the Gauss law means associated with that particular object inside through which those electric field lines are passing. So this was all for today. On the next lecture, I will be uploading the exercise questions of this chapter. So if you like this video, please like, comment, share, and do share with your friends. And if you feel any doubt, please do comment in the comment section. Thank you.